Okay, friends, as you know, our lecture on Friday, I forgot to record the sound. So this is a re-recording of Friday's lecture. And hopefully I don't miss anything that we talked about in class. If I do, you can catch the actual notes from Friday's lecture on the content page of Learning Suite. So we've been talking about the wave function and how in order for it to obey the anti-symmetry principle, or the anti-symmetry requirement of the Pauli principle, we have to formulate our wave function as a Slater determinant. And we talked about how the Slater determinant means that in a molecule, say with 4 electrons, all 4 electrons contribute partially to the orbital phi 1. Similarly, electron 1 contributes partially to phi 1 bar, which has different spin, phi 2, and phi 2 bar. This is related to the principle of indistinguishability. We can't tell one electron from another, and so each orbital contains an overall contribution of 1 electron, but actually each electron in the molecule is contributing to that orbital. Now, we're going to determine the energy of this molecular wave function by applying the Hamiltonian to the wave function, multiplying by the complex conjugate of the wave function, and then integrating over all space. We've noted that our Hamiltonian contains a kinetic energy component. This is the second derivative of the wave function, which when multiplied by minus h bar squared over 2 times the mass of the electron will give you the kinetic energy of a particular electron, and we'll do that for all of the electrons in the molecule. We also have a favorable term for attraction between the nucleus and an electron, Coulombic attraction, which depends on the distance between the electron and the nucleus. Note that both of these terms only operate on the position of electron I. You only need to know about 1 electron there. So we're going to call this the 1 electron operator. We'll combine them both into this term H, core, the core Hamiltonian, the core 1 electron Hamiltonian. The second part is electron-electron repulsion, which you need to know the positions of 2 electrons because you need to know the distance between the two. So we'll treat these two operators differently. We're going to apply the Slater determinant to the Hamiltonian, and from that we're going to get the Hartree-Fock equations. So in the Hartree-Fock equation, instead of dealing with the overall molecular wave function, when we apply this molecular wave function, when we apply the Hamiltonian to that wave function, we actually can separate out the individual 1 electron wave functions. So this term HII represents the core Hamiltonian applied to the wave function for electron I. So in this case, H11 would be, we take electron 1 in phi 1, we apply the core Hamiltonian to it. That gives us the kinetic and potential energy of that electron, potential energy with respect to the nucleus, and then we multiply that by the complex conjugate. That gives us that energy term. This second term with the J and the K comes from the 2 electron operator that comes from electron-electron repulsion. And in order to understand this better, we're going to need to do just a little bit more math. So let's make things simpler at this point by writing out the Slater determinant for a molecule with just 2 electrons. All right, so our wave function for a molecule with 2 electrons. Here is a normalization term, which you don't need to worry about it. It just guarantees that the overall molecular wave function squared equals 1. We have orbital phi 1 with electron 1 in it. and here orbital phi 1 with electron 2 in it. Similarly, orbital phi 1 bar with opposite spin with electron 1 in it, and orbital phi 1 bar with electron 2 in it. And if we expand this out, we get, based on the rules for determinants, phi 1 with electron 1 times phi 1 with a bar with electron 2 minus phi 1 with electron 2 times phi 1 bar with electron 1. So in this Slater determinant, we have a non-permuted term, meaning the electrons of 1 and 2 are where they were to begin with, and then we have a permuted term where we've exchanged the positions of those two electrons. Now let's see what happens when we apply the Hamiltonian to this wave function. So I'm going to copy this, and here's our integral. What I've written here is just an expansion of the following integral. We're going to apply our Hamiltonian to this wave function and then multiply it by this wave function and integrate over all space. Now, one thing to remember with integrals, you can separate them out with pluses and minuses. You can separate an integral of a difference into a difference between two integrals. So what we're going to do is apply the Hamiltonian to each of these terms separately. And then we're going to multiply each of those terms. So this is the Hamiltonian applied to the first term there. And this is the Hamiltonian applied to the second term. And then each of these two are going to be multiplied by first this term and then this term. So we're going to end up with 4 different terms. So if we apply phi 1 with electron 1, phi 1 bar with electron 2, and we apply that to this integral, we get the term listed here. We might call this the let's use i's and j's sparingly. And then if we apply this first term to this integral, we're going to get phi 1 with electron 1, phi 1 with electron 2. Okay, and similarly, we can take this negative term here and apply it to both of these brackets. So negative phi 1 with electron 2 times phi 1 bar with electron 1, and then negative here times a negative there would be a positive, and this would be phi 1 with electron 2 times phi 1 bar with electron 1. Okay, so if we look at what we have here, we've got 4 different terms that come from expanding this Slater determinant through the Hamiltonian. This term is a non-permuted integral. And so is this one. In contrast, these 2 negative terms are permuted integrals. What do we mean by that? Well, the Hamiltonian gets applied to one thing, but the thing that gets multiplied to that Hamiltonian has the electrons in different positions. Notice in front of the integral, in front of the Hamiltonian, electron 1 is in phi 1. After the integral, electron 1 is in phi 1 bar. So that's a switch. Sometimes these are called exchange integrals instead of permuted integrals. Okay, so let's focus in on the 2-electron operator part of the Hamiltonian. You'll have to take my word for it that when you apply the core 1-electron Hamiltonian to each of these permuted and non-permuted integrals, anything that's an exchange term disappears because this is simply a 1-electron integral. But let's deal with the 2-electron operator where we need to know the positions of both electrons. So let's go ahead and copy what we've written here, but let's apply it to the 2-electron operator. And in this in this discussion, we're going to leave the constants out because you can factor constants out of an integral. So the constants are going to be implied. So let's write down our non-permuted integrals. Phi 1 with electron 1 in it, phi 1 bar with opposite spin with electron 2 in it, 1 over the distance between our electron 1 and electron 2, and then here we have phi 1 with electron 1 in it and phi 1 bar with electron 2 in it. This is going to be this integral is going to give us the Coulombic repulsion between electrons 1 and 2. And we'll actually call this a J integral, J1, 2. Okay? And we could get that same thing from the other non-permuted integral in which electron 2 is in phi 1 and electron 1 is in phi 1 bar. Again, we're going to use the distance between electrons 1 and 2, and on the other side of the integral, again, we have electron 2 in phi 1 and electron 1 in phi 1 bar. And we'll let that equal J21. And of course, J12 should equal J21. Okay, so that's where the J integral comes from. That represents Coulombic repulsion between electrons 1 and 2. Okay, now let's look at the we've looked at the non-permuted integrals with the 2-electron operator, which is 1 over r electron I between electrons I and j. Now let's look at the permuted integrals. let's apply the 2 electron operator 1 over Rij to the permuted integrals. And remember, the permuted integrals involve a change in location of electrons 1 and 2 before and after the Hamiltonian. So we have 2 permuted integrals. Let's look at this one first. So that was negative phi 1 with electron 1 in it, phi 1 bar with electron 2 in it, the operator of 1 over the distance between electrons 1 and 2. But on the other side of the integral, now electron 2 is in phi 1 and electron 1 is in phi 1 bar. Some people struggle to know, does this integral have a physical meaning? And the answer is difficult to say, but it comes from the fact that the Slater determinant generates these permuted terms where electron positions are interchanged. So this is an exchange integral. Now we can write out the other one just for completeness. That other term here, and in that term we start with, let's see, electron 2 being in phi 1 and electron 1 being in phi 1 bar. The operator is 1 over the distance between electrons 2 and 1, but then on the other side of that operator we've got electron 1 in phi 1 and electron 2 in phi 1 bar. Notice that these exchange terms are both negative because in our Slater determinant the permuted term is negative. Okay? So it turns out, if we look at these 2 integrals, the j integral and then this is the k integral, it's the exchange term, k12, k21, we would expect k12 to equal k21. Spin affects these 2 integrals differently, and we need to think about that. And so let me actually give ourselves a little bit more space by moving this down a little bit. Recall that our representation of electron 1 in phi 1 can be split up into a product of 2 parts. Spatial wave function with electron 1 in it multiplied by spin wave function alpha with electron 1 in it. Similarly, we might say that phi 1 bar with electron 2 in it is equal to theta 1, same spatial distribution with electron 2 in it, but in this case opposite spins, so beta spin wave function with electron 2 in it. Now notice that this operator 1 over r, which is the distance between the 2 wave functions, that only requires knowledge of the spatial wave function. It doesn't operate on spin. And so that has the consequence that we can factor the spin terms out of each of these phi 1 and phi 1 bar wave functions. Let's see how that would work for the J21 integral that we've just written. And let me just move this down a little bit. Okay, so let's rewrite that J21 integral with the spin and spatial wave functions written out separately. So theta 1 with electron 2 in it and beta spin times theta 1 with electron 1 in it times alpha spin, 1 over our distance between two electrons 2 and 1. And then on the other side, we've got theta 1 with electron 2 in it with beta spin, and then theta 1 with electron 1 in it, but with alpha spin. Now remember, because the operator doesn't operate on spin, we can factor those spin terms out. So J21 equals beta with electron 2 in it, and then we multiply that by the spin term over here that has electron 2. That happens to also be a beta wave function. And then we do the same thing with the alpha wave function with electron 1 in it, and we factor out also this electron 1 term, which happens to have alpha spin. And then what's left inside the integral is just electrons 1 and 2 in spatial wave function theta 1, distance between electrons 1 and 2, and then after the integral again, spatial wave function 1 with electron 2 and with electron 1. So notice that because the spin terms are the same on either side of the operator, when we bring them here, a wave function multiplied by itself and integrated over all space is equal to 1. And that's because of the normalization principle. Okay, so spin actually factors out and goes to 1 in the J integral, the non-permuted integral. Let's see how spin affects the permuted integrals. Okay, and let's just take this first term, minus k1, 2. And again, let's separate out our wave function, phi wave functions, into spatial and spin components. So spatial wave function theta 1 with electron 1 in it, and with alpha spin, and then multiplied by spatial wave function 1 with electron 2 in it, and where electron 2 has beta spin. The operator is the 1 over the distance between wave functions, between electrons 1 and 2. Then after that operator, we have spatial wave function 1 with electron 2 in it, with that electron 2 having alpha spin, and then spatial wave function theta 1 with electron 1 in it, with electron 1 having beta spin. Again, remembering that the operator doesn't operate on spin, and therefore the spins can be factored out of the integral as constants. So let's see what that does. We factor out first the electron 1 terms before and after the integral, or before and after the operator. So we would have alpha 1 times beta 1 integrated over all space. Then similarly, we would have beta 2 times alpha 2 integrated over all space. And then what's left over here is electron 1 in theta 1 times electron 2 in theta 1 times the operator of the distance between electrons 1 and 2. And then on the other side of that operator, we have theta spatial wave function theta 1 with electron 2 in it times spatial wave function theta 1 with electron 1 in it. Now, alpha and beta spins, up and down spins, are orthogonal to each other, which means this term must equal 0. There's no overlap between alpha and beta spins. which means this k term goes to 0 whenever electrons 1 and 2 have different spins. Okay? Well, can we imagine a situation in an electron where two electrons would not have different spins? And to do this, let's look at a permuted term from a larger molecule. So let's return to the wave function we had at the beginning. This is a 4-electron. This is a molecule with 4 electrons in 2 different spatial orbitals. So what we'll do here So our question is, what happens to the k integral term when electrons I and j have parallel spins? So let's look at a term from let's look at a term from the 2-electron operator. Let's look at an integral from the 2-electron operator, and let's say we're thinking about electrons 1 and 3 in this molecule. And this will be an exchange term, so it'll be negative. In front of the integral, let's imagine we have phi 1 and phi 1 bar with electrons 1 and 2 respectively, and phi 2 and phi 2 bar with electrons 3 and 4 respectively. Electrons 1 and 2 have opposite spin. Electrons 3 and 4 have opposite spin. And let's have the particular integral we're looking at involve exchange of the positions of electrons 1 and 3. You will have to sort of take my word for it, but this integral term that I'm writing out at this point, you would get as one of the terms if you expanded out this Slater determinant and wrote out everything. So on the right-hand side of the integral, we have positions of electrons 1 and 3 exchanged. So this is an exchange integral. We would call this minus k1, 3. Notice that our operator here only operates on the positions of electrons 1 and 3, so we can factor out the wave functions for electrons 2 and 4. And those are just going to go to, those are just going to equal 1. Based on the normalization principle. And then left inside the integral, we have phi 1 with electron 1 in it times phi 2 with electron 3 in it, multiplied by the operator 1 over the distance between electrons 1 and 3. And then on the other side, we have phi 1 with electron 3 in it and phi 2 with electron 1 in it. Okay? So our minus k13 equals this exchange integral term. I don't really like how I wrote that there, so let me make it a little bit better. Now, as we did before, let's split up our phi 1 or phi 2 wave functions into spin and spatial orbital components. In this case, phi 1 is spatial orbital 1 with electron 1 in it times with alpha spin. And then phi 2 with electron 3 in it is spatial orbital 2 with electron 3 in it, and electron 3 has alpha spin. The operator will be 1 over 1 over the distance between electrons 1 and 3. And then on the right-hand side of our operator, we'll have spatial orbital 1 with electron 3 in it with alpha spin, and spatial orbital 2 with electron 1 in it also with alpha spin. Can you see what's going to happen here? If we factor out the spin terms because they're constant with respect to this operator, if we factor out the terms for electron 1, before the operator, electron 1 had alpha spin. On the other side of the operator, electron 1 had alpha spin. So that matches. So instead of going to 0, that term is going to go to 1. And then here, for electron 3, before the operator, it had alpha spin. On the other side of the operator, it has also alpha spin. So that term goes to 1 instead of 0. And then we're left with theta 1 with electron 1, theta 2 with electron 3, operator 1 over the distance between electrons 1 and 3, and then theta 1 with electron 3 times theta 2 with electron 1. So when electrons have parallel spin, we get this exchange term that's non-zero for electrons with like spin. And the term is negative, that is favorable, when electrons have parallel spin. So this is the origin. This is the explanation behind Hund's rule. Hund's rule says that, for example, if you're in a situation where you fill up orbitals one electron at a time with parallel spin first. So if I were filling up these 5 orbitals with 7 electrons, the Hund's rule says it would be more stable for these electrons to be parallel, and that is because of the K integral. What this tells you is that electrons with the same spin don't move independently, and there's a favorable, there's stabilization, there's favorable energetics when electrons have parallel spin. So if we go back to the Hartree-Fock equation, we can start to understand where these terms come from. The core integral, HII, should give you the energy of 1 electron kinetic energy of 1 electron plus attraction between that 1 electron and the nuclei. The J term gives you Coulombic repulsion between electrons I and J. The K term offsets that somewhat. It's stabilization for I and J with parallel spins. It's only non-zero when the spins are parallel. So one thing you could ask at this point is, why are we multiplying the Coulombic repulsion by 2, whereas the exchange integral K that you get for parallel spins is negative? It's favorable, but it's not multiplied by 2. And the reason for this is, if you think of electron I and a nearby electron pair with J and maybe K, I don't know. think about the number of ways there are to repel between I, J, and K versus the number of parallel spin interactions. So in blue, I'm going to show the places where there's repulsion. So this would be J, I, J. This would be J, I, K. So two repulsion terms. And this would give you, and because J and K are in the same spatial orbital, I'm sorry, forgive me. These subscripts in the I should point out that these subscripts in the Hartree-Fock equation refer to spatial orbitals. So you have two electrons in this is orbital J, one has alpha spin, one has beta spin. So you've got two repulsion terms, J, I, J, but you only have one non-zero K, I, J. If you tried to do the exchange term between the alpha and the beta spins, that would go to 0. So the reason you've got 2 in the Hartree-Fock equation is there's twice as many ways for repulsion as there are for having parallel spin. Okay, therefore what? Who cares? And for a molecule, why did we do all of this? Well, we wanted to know what the wave function is for our molecule, and we wanted to know what the energy of that wave function is. By applying the Slater determinant to the Hamiltonian, we've split up that complicated equation for the wave functions for the whole molecule into individual equations for each individual one electron wave function. So we want to know what the energy is of each one electron wave function, and we want to know what those wave functions are. But in order to know what those wave functions are, we have to be able to calculate the core integral and especially the J and the K integrals. And remember, the J and the K integrals are going to require me not only to know the wave function for electron I, but the wave functions for all the other electrons in the molecule, because I've got the repulsion between electron I and all the other electrons in the molecule, and then I have this bonus term where there's parallel spins. So I need to know the wave function. I can't get the wave function without the J and the K integrals, but I can't get the J and the K integrals without knowing the wave function. But I can't get the wave function without knowing the J and the K integrals. But I can't get the J and the K integrals without knowing the wave function. But I can't get the, and you see where we're going. Sorry, this is we're in a situation where we can't solve for the wave function analytically, so we're going to have to use an iterative process, a numerical iteration. So how do we solve for the wave function and its energy? We iterate. We guess what the wave function should be. We calculate the core and the 2 electron integrals. We get out a new estimate for what that wave function should be, and then we do it again until the answer stops changing. And our goal will be to minimize this energy. So we want to arrive at the wave function with the lowest possible value for energy. When that happens, we say that our wave function is self-consistent with the field generated by all the other electrons. And in this way, by treating each electron individually and iterating until it stops changing, we calculate it as though each electron is interacting with a static, non-moving field of all the other electrons in the molecule, self-consistent with the field generated by the other electrons. And this approach, self-consistent field, is called self-consistent field theory, sometimes abbreviated as SCF. And if you use the Hartree-Fock equation, it's the Hartree-Fock self-consistent field theory. Now, this theory treats all the, in calculating the wave function for electron I, it treats all the other electrons as static. Of course, that is not actually how molecules are. Electrons are in motion, and they can correlate their movement so as to minimize electron-electron repulsion. So if you obtain an energy for a wave function from Hartree-Fock self-consistent field theory, that energy is always going to be greater than the actual energy for that wave function. And this gives us something called the variational principle, which tells us if we can minimize this energy, we'll have something that's as close as possible to reality. The difference between the energy of a wave function in reality and what we measure, or rather what we estimate from Hartree-Fock self-consistent field theory, is called correlation energy. And this has to do with electron-electron correlation lowers the repulsion from the J integral as electrons move in concert to minimize Coulombic repulsion. So this is important because the ability of electrons to minimize their movement, to minimize Coulombic repulsion through correlation, is related to some important phenomenon that Hartree-Fock and self-consistent field theory do not take into account. So in class, I mentioned that one of the things that we are interested in as physical organic chemists is non-covalent interactions, and one of these is van der Waals interactions or induced dipole interactions. I'm trying to represent the electron cloud surrounding both of these molecules, and the electrons on the molecule on top can correlate their motion with the electrons on the molecule in the bottom so as to generate instantaneously complementary electric fields. That is, our molecule can arrange itself so that instantaneously we have an excess of negative charge on one side of the molecule and an excess of positive charge on the other side of the molecule. This fluctuates, it's not permanent, but that motion in one molecule can be correlated with the motion of electrons. I'm struggling with my signs. That can be correlated with the motion of electrons on the other molecule in a way that attracts the two molecules together. And though you would expect this interaction to be weak, it can have dramatic consequences. For example, as I said in class, this is why wax crayons are solid, and it's why geckos can climb on surfaces without any adhesive at all. So there will be situations in which you'll want to account for electron-electron correlation. And in those situations, you'll need to use higher levels of theory. We won't go into this, but there are other kinds of theory which your text explains in a little bit. If you have need of them, you can go look them up and learn more about them. Density, functional theory, MP2, and CCSD do account for correlation. Some are they do it in different ways, and some are more appropriate for some context versus the other. A student asked in my office on Friday afternoon, how do you know what method to use? And the answer is, it depends on your application, and the best way to know what you should be using is to look at the literature and see what other people have used for similar problems. And there are other resources you can use to see what each sort of theoretical method is specialized at doing. But one of the ways to get started is to just see what other people who've been working on similar problems have done. At this point, we'll end in the lecture. In class, I showed a little bit about how to use Gaussian, though I've made a tutorial video that shows how to do that in detail, so I won't repeat that here. With that, I will see you next time.